All right, welcome back, everybody. Today, we are continuing on with 7.2, and at the end of class... What just happened? I just had a paper staple itself to another piece of paper just because the loose part of the staple. That's odd. Strange. Anyway, sorry. Last class, we were talking about some of these dilations, and I left you guys with this one singular wonderful problem. And what we decided yesterday was if we're composing these things, and we just jumped right in with an example, we reviewed a little bit, and we said, hey, here's what we do first. How does this rule work? Because I didn't tell you guys yesterday. I asked you to check your notes because we've done this extensively. How does the translation work? Anybody feel comfortable in kind of walking me through that one? Ashley, how does a translation work? Good. So if I do 3 plus 1, it takes me to 4. And if I do 5 plus negative 2, it takes me to 3. If you did this problem, did you get that as your intermediate step here? Fantastic. Where's y prime then? 0, 2. I agree with you. And z prime? 2, 5. Do we all agree? Now, Carson asked a good question. You were gone earlier this week, so it's reasonable that that question exists. What's D2? And then normally we would give one more thing here. I would give you the center. If it's not listed, do we have a safe assumption? And what is it? The origin. How do dilations work if you're just doing it from the origin? You literally just multiply. So when we get to this, and I don't love calling this x prime, but I don't have a good alternative. We get to x double prime, our final image. This is where we're trying to get to. And where does this one go? If we scale it up by a factor of 2, does it get bigger or smaller? So where would my new final image point be? 8, 6. Because it's literally just taking this and multiplying it by 2, and it works so nicely. How about y prime? So I get why you would say 0. Do you see why it's not 2? Okay. 0, 4. And last but not least, where do we go? 4, 10. Now, as we work through these, how did this one feel, first of all? Not great. Or it felt fine. Okay. So as we're looking at these, I should probably get into the right chapter first and foremost. I don't think we're going to get like wildly challenging with a lot of these things. And like if you're comfortable with this, I think you'll be comfortable with the other ones with a few little small exceptions. If we're trying to do compositions, this one is the first composition that we did here where we composed a translation and a dilation. Instead of a Instead of a translation, did I have some other options for things that we could have done? Like what? I could have done a rotation, or I could have done a reflection. Now, that all sounds fine and dandy, and I think that everybody in here could have answered that question. And I'm pretty confident with that. What I don't know if everybody can answer is a question if I say, what's the rule for rotating 90 degrees, or 180 degrees, or 270? Or what's the rule for reflecting over the x-axis or the y-axis? Do you guys have all those just right up here ready to go right now? And that's okay, right? Because if you don't have them physically, it's not physical, that's a weird way to word it. If you don't have them accessible right here, right now, where would you have access to them? Your notes. Like, we don't take notes for fun. I mean, we do take notes for fun, and it is really fun, but it's not the only reason that we take notes. Cool. So, looking at this next problem, we are going to give ourselves a nice definition. And I don't know that I really agree with the way 100% that they approach this. When we started congruent stuff a long time ago, remember we had a way to do it. The first way that congruence was introduced was saying, was there an isometry or a rigid transform that takes me from one to the other? And it's awesome if we can find that rigid transform. And there's value to doing it. But eventually, instead of doing just, does this side of the triangle or does every point transform somehow via rotation, reflection, or translation, the question changed. Can we find all three sides are congruent and all three angles are congruent? And then we started developing some awesome shortcuts like, gosh, I don't remember any of our congruence shortcuts for triangles. If only Raylene remembered one of my 4 triangle shortcut congruences. And I don't want no talking back. Indeed. No set. Yeah, SAS, right? Side angle side. Give me another one, Vincent. Side, 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 right? Snake jazz. Side, side, side. What else? Ace. Something. I don't know the moves. And then there's one more. ASA. ASA. And all of those are shortcuts for congruence, right? Would you prefer using the fact that we know what congruent means, or to show that there's a single rigid transform or composition of single or of composition of transforms that takes us there? Which one did you prefer? Side angle side and using those shortcut stuff, and I don't know if they're really shortcuts necessarily, or just showing that exists a transform between them. I'm losing you because I'm struggling with my words. Let's see how it goes. And we're going to approach similarity the same way. We're going to see that, hey, and we'll get a definition real quick, and we'll make sure that we see why this is happening. But all we did so far was we just started building an example in here, and it's a good review. For today, we're going to start talking, and we'll see these. Congruence, just kidding. We're not talking congruence, we're talking what? Similarity. Real quickly, what's a shorthand symbol for similar? A tilde. So when I write similar, you can write similar, but you could also write the tilde. We're going to write this as a definition, and it's not caps, so my bad. We're going to define for ourselves similarity transform. Now, I've already made a mistake, and it should just say similarity, but that's okay because we can make this work, and it's the same idea. If we said a congruence transform is a rigid motion that just moves something from one location to another and every point matches up, that's how we talk about congruence. A similarity transform is going to move every point in a different way, though. And we should move in a different way because we're no longer congruent. So we'll say a similarity transform is a transformation and I'll say in here or composition thereof. And I think I can probably just say or composition, and it has the same meaning for our purposes. A transformation or a composition of transformations that maps every point of one figure to another location. Now, when we say this, there's some ambiguity and some chances to this definition doesn't quite cover it. And we're going to pause here for just a second. We're going to have a little bit more to write about it. But with what we've written right now, do you think it truly gives me an idea of what similarity transforms do? Anybody feel like with this definition, you can make sense of what similarity means? Thumbs up, thumbs down. Like I don't need enthusiastic yeses and nos like you've been giving me so far. I just need to see some sort of indication. Okay, fair. There's a part of this that I don't like because when I just say to another location, I just want to see what could happen. And you don't need to sketch this. I just want to talk about this one. If I don't specify that there's a rule that's followed, could I take this point and do it up to here? Like that's been mapped to another location, right? Could I take this point and map it up to here if that's all it says, it's to another location? And I can do the same thing here, and I'll just map this one here. Did I do exactly what this said? Every point from one figure to another. Now, we're missing something because I don't know about you guys, but I don't know that I think that those two really look that similar, although that's way closer than I meant it to be. If I obnoxiously move one of these, so it is certainly not the same, like maybe this point is up here instead, are these the same triangles, even though I moved every point to another? No, they don't even look the same shape. They're both triangles, but there's something missing here. We need a transformation or a composition thereof that maps every point of one figure to another location, or another figure, we could say, such that something gets kept the same. Now, if I give you a true similarity transform, which we've only seen one that standalone is what I would consider a true similarity transform, what's the only of all of our transformations that changes the size but not the shape? Dilations are the only ones that we would say like are 100% a similarity transform. Now, when we look at this, if I give you a shape and I'd say, like, here's a dilation, there's one thing that I've asked you over and over and over to find for me. If I want to know more about a dilation, what's the one other piece that you always need? The scale factor. How do you find the scale factor? So that can be a bigger question. There's multiple answers. Whether there's a few different answers that I'm expecting and hoping to hear. I'm going to give you guys 60 seconds. We're going to do the one of you speaks and the other one doesn't. So somebody is going to be either really lucky or really unlucky, depending on your point of view, because we have an odd number of people, which means somebody gets who for their partner? You. I'm not going to ask for volunteers because I am a weak emotional being and I don't want to cry in front of you. So what I want you to, that was a joke, by the way, just so you know. Lots of clear laughter. What I want you guys to do, one round of rock, paper, scissors with your neighbor or your partner. Carson, it's either with Vincent or Ashley. I don't mind whoever you would rather go work with there. Rock, paper, scissors. Whoever wins gets to decide, are you going to use the next 60 seconds to explain what else we need or how to find a scale factor? Or is it your neighbor or the loser of that game who's going to give that explanation? So one round of rock, paper, scissors. Who are you going to go work with? I mean, you could also just work with me if you just want to stay here and I can make Vincent move. Okay. So, you two. All right, here we go. Pick a rock. All right, I want you to talk. I did not know. I was really curious if you were. All right. So, once you have a winner, decide if you're speaking or not. How do you find scale factor? It's the question Lily said just a moment ago. But if we get all of these to be the same side or same ratio, we will say we want every point to move to another location such that each side is proportional. Which we'll clean this up. Proportional just means the same ratio. We need each side proportional to the corresponding side. And I could have cleaned this up better. Corresponding side. And I have to sneak in a few more words, I'm sorry. Of the other figure. Because I didn't specify whether we're at the image or the pre-image or anything like that. But what we require to ensure that all of our sides move in the same way is that whatever we do, we wind up proportional. Now, the cool part about wording it like this is we don't have to say just through some dilation, because it could be a dilation and a rotation or a reflection. It doesn't matter. A prime, B prime, no matter where it orients itself to, will match up with AB, their corresponding sides. And they're going to have that same ratio. Now, for this, proportionality is the big deal. We've actually been finding the proportionality or the proportion between them, and we just called it a different word. We've been saying the proportional relationship between the image and the pre-image is called the ratio, but we have a name for the specific ratio when we take A prime, B prime over AB. Scale factor. We are finding the proportion between these figures, and as long as it's the same everywhere, we're good. Like, that's what it requires. So when we're looking at these, one of the things that we do, and we'll pivot away from this in the coming lessons, but the first example is I just want to check, if I give you some similar figures, can we find transformation or a composition thereof that does it? So I will put this picture up and I'll say where you want to find this, but I'm just going to say find a transform, find a transformation or composition of transformations, which I'm just going to say or composition, that maps the following. And then we're going to get a picture, and I will give you where this is, and we'll do a couple of these. Our first one, just so you guys, if you want to see it in your text, I'll put it up on the screen. But if you don't want to have to draw it right this second, you will find this on page 315. And it is example 2 on page 315. I'm going to put it up on the board for us. And I'm actually going to, while you guys start playing around with this, because I'm going to give you a minute, I'll get some other stuff set up. So for now, here are the figures that we're dealing with. And all we want to know is there a similar, are there transforms that get us from here to there? And if we can find them, then we're awesome and we have a similar transformation or a similarity transform. But right now, all your job is with these, and I'm trying to hide the answers, and I'm going to get the online part up here in just a second because I really like that. I want you guys to see with your neighbors, is there a specific transformation that'll take me from the image to the pre-image? Now, because we change the letters, it's harder to tell whether or not they really are like what goes where. So I would pay careful attention to this little part. I'm going to give you guys like 2 minutes, roughly. I want to see if we can't find a way to make this happen. Sweet. Everybody know what I'm asking for. So just to highlight, I'll show you a wrong answer. Somebody could say, I think you translate this 2 to the left, and we end there. That doesn't happen, right? So maybe it's a translate and a dilation, or maybe it's a rotation and a dilation, and maybe there's a few different ways we can do this. I want to see if we can find, are we going black to red or red to black, I guess, first? How do you know that? So Carson is right, but other than just a gut feeling, is there any way that we can confirm that black is the pre-image here? What's the mistake that you've seen me make on the homework over and over again that I say I'm not going to make anymore? To reading directions, right? Anybody maybe make the mistake of not reading the very top line there? From XYZ to JKL. Black is a pre-image. You're right, Carson. All right, I'm going to give you guys a minute. I want you to see if you can't find a single or multiple transformations that take me from this image, sorry, this pre-image to this image. Cool. Instead of just using those, you suggested we do something else. So is that what you told me first? Okay, so Carson noticed that it got bigger, and he found the scale factor as 2. And Carson found the scale factor, this proportionality constant, by checking this over this, which works. But we could also check this distance over this distance. And I know it's ugly because of how zoomed out I am right now. But if I zoom in and we look and see that we do actually get some nice points here eventually, I can see that if I go from the origin to X, 2 over and 1 vertical. If I go from the origin to J, where I think it's going to have to wind up, we go 4 over and how many vertical? 2. So we see a scale factor of 4 to 2 or 2. If I were to just check this length, what is that length? 1, 2, 3, 4 over 2. Do I get the same scale factor? They're proportional. And I could check that with all these sides. Now, eventually we'll get to just using that proportionality idea, but we'll start with our lovely transformations. So Carson said that he saw a rotation. Now, Carson, I think you gave me this answer. Anybody know how much we have to rotate by? 180. Now, what's cool about this is we're just going to start checking. If I rotate and I go 90, it takes me here, which is what I would expect. And if we go 180, let's just check. We're almost there, almost there. If we go to 180, not 185, not 185. Oh my gosh. Are we oriented correctly? Awesome. But we're not there yet. What else did we have to do? And I think I went the exact wrong direction, to be honest, because I think you said dilate first. But if I rotate first and then dilate, so here we're getting a little bigger, a little bigger, a little bigger, a little bigger, a factor of 2. Are we able to take this figure and through compositions, map it directly to this? Absolutely. If we can find these transformations, what do we conclude about these 2 figures? They are all proportional. Are they the same shape? Are the 2 figures that we started with exactly the same size, though? So they're definitely not congruent, but we can successfully now say that they are. And there's another word, an S word. Similar. Okay, now looking at these, just an interesting kind of follow-up question. I did it the exact backward way that you had told me just now, and I don't know why I did that. I rotated first and then I dilated, right? What if I had done what you had told me to initially? If I dilate by a factor of 2 first, is it still going to work? If I dilate by a factor of 2, I wind up all the way over here. And then now we can just rotate that 180 and look at, I get the same thing. So for this specific situation, that was a bad one. Does it really matter which one happened first? No. So if it doesn't matter, we could translate, like we could switch these around. What's it called if it doesn't matter the order it happens in? Like somebody gets up in the morning, they brush their teeth, they shower, they hop on the train, they switch platforms, they hop on another train, they hop on the bus. They have a 2-hour what to work? And this, you'll know it as soon as we just give it away. If somebody says, gosh, I hate my commute, what are they talking about? Okay, so that's all right. We don't live in a big city and nobody here has to commute. It takes me 90 seconds to get here and I don't have to drive. So that's fair. Commute is to move, like to travel. Is there a property that has commute in it that you guys have ever seen? What is the commutative property? Yeah, like check this out. What's 2 plus 6? Hold on. What's 6 plus? Hold on. 63 plus 4. There we go. Okay, what about 4 plus 63? Hey, did it matter which way we did it? Addition's commutative then. Are these transformations seemingly the same? Yeah, they're also commutative. Now, we are branching and so close to being able to talk about some big math ideas that unfortunately you're like 4 or 5 years away from really being able to dive into, but we are on just the doorstep here. Super hard, super easy. So for this figure, what I would like us to do, just to make sure, because we can all see it here, and it's weird to not have the example like here drawn. If you drew it, cool, but you can look at it. We'll say, yes, there exists, and I'm going to say the transform exists. And what I would like us to do is I don't want us to lose the notation stuff. I want to make sure that we can say this. And I will help us out. We are going to take triangle, and I forgot the letters that we were working with already. Triangle XYZ, and we're going to do something to it to make it become, I don't know why I used lowercase, that was bizarre. Triangle XYZ, something gets made done to this, or some transformations are done to this, that take us to triangle JKL. Now, there's a little awkward space here that I am going to write something in. And what were the two operations that we just did to this thing? Rotate and dilate. Does it matter which one's first? No. Which one do you want me to write first? On the left. Sure. Oh man, I don't remember. How do I write down I'm rotating? R. How much did we rotate just now? 180 degrees. Okay. And about what? The origin. Now, I think we should just agree with the following convention. If we have a center of rotation or dilation and it's the origin, we're just not going to include it. If we all agree that that's okay for us. Okay, so we rotate 100 degrees and this is composed with, what was the other operation we needed? And oh man, how do you write dilations? Uppercase D, and what was our scale factor? 2. What was the proportion between the sides of the image and pre-image? 2. It's the same thing. The proportional relationship is what we're after. Okay. Interesting. I did not read the follow-up to this is, what if we do it in the other way? And it was pure happenstance that I did the same thing. So me and your authors have apparently both taught math before. It's good news that your authors also teach math. All right. So as we're looking at these, do we want a challenge question? Are you sure? How sure? But not 100? Okay, I'm trying to mess with Ashley and all of you, but nobody's really messable today. Okay, for this one, up to you if you want to write them. You know what? If I have the book open, I might as well just be doing these ones. That makes way more sense. So I'll just show it up here. We're going to look at another problem from the text, and eventually I'll find it. There's got to be a 7.3 somewhere in here. Example 3. You guys shout it out when you see it. That's fair. All right, so example 3, we're going to go over to the try it instead. And in hindsight, definitely faster if I just use a document camera, but I'm learning. So let's check out the next one. Here's my question for you, and we'll do this one. I want you to tell me, is there a similarity transform that exists between these? Is there a way to map black to red? And if there is, you're not going to be able to give me like the specific values and things since we don't have coordinate here, but we can estimate at least from this. Are they similar? And if they are, what transformations take me from here to here? I'm going to give you guys a second. I'll keep it up on the board. If you want, this isn't your textbook, it's example 3 from section 7.2, and it's the try it problem underneath. Tony, will you go get me a drink of water? I'm super thirsty. Like I'm just parched. I just need a drink from the fountain over there. Do you have your text? Okay. Feel okay with this, or is it meh? Okay, the text will help if you're struggling with it. What do you guys think? I'd say it's probably about a half, yeah. Ooh. Ooh, a reflection. Why can't it be a rotation? You're right, just so you know. If I tried to rotate this, and I like what you're thinking, like this would probably be about the center, right? If I was trying to rotate it. Notice my finger's on W. If I rotated, W would be over here, and it won't work, right? So I can see it's not going to work there. Okay, what do you guys think? Give me a, I don't know, what's a woohoo if you think this is similar. Too much energy. Tone it down a little bit, please. Okay, so as we're looking at it, I do also agree, I think. Like, we can't really check for sure unless we want to measure stuff. I think they're the same shape, different size, different location. First off, Toddy, if we look at this one, if I go from black to red, is it getting bigger or smaller? So if it's getting smaller, do we call that a reduction or an enlargement? Good. Yeah, love it. We've reduced. Now, I can't tell exactly what it is. I have an estimate, but I can tell you if it's a reduction, we all know something about the scale factor. So less than 1 for sure. And I do think I agree with you. I think it's about a half if we were to measure this. Can we all agree with that? So we scale this down by a half, and all of a sudden, since you are all here, I lied. I have to do it on here so that somebody can watch the video if we don't get videos. So let me get this real quick because I want to draw on this. I really wish that Chrome would let me draw on the screen, like mark it up as if I were just drawing. That'd be so convenient. I'm going to write a letter. Okay, if we scaled this thing down. Now, would you guys dilate first or rotate first, just out of curiosity? Does it matter? I said rotate. I definitely don't mean rotate. We'll get there. Dilate or reflect first? Reflect. Okay, so I'm just going to eyeball this out. Now, the cool part is if we didn't want to eyeball this out, we do have a way to make this work. I know that Z maps to Z prime, and I'm going to do some pink lines just to help me align this a little bit better. I know that that maps to that, and that when I reflect, they're going to be equidistant. So what I'm seeing right now is that I think my line of reflection, and I'm just eyeballing it, is about here. If I gave you this shape, and I just said, here's Z, and I said, hey, here's a graph and a protractor, how do we reflect this, like accurately and well? Anybody recall? So we count the distance from this to the point, right? Now, check it out. I'm going to count, and I know we can't really count. This distance is awesome. Ashley, your face is what I wanted to see. The face you made is what I was hoping everybody would do just now. Why did you grimace when I said this is the distance? Yeah, who on earth measures distance like this? How do we all measure distance always? So that's straight. That's a straight line. Vertical? I don't know if I agree with you because this can certainly reflect to here, and now it's not vertical. I know on this one it was vertical, but there's a more important word that I'm after. So this one's like probably been dead. You guys, I don't even know if you had this. Several years ago, if somebody's doing something good, I think they were pushing a letter. Ooh, what is that letter? P. So I don't even know what it means, but pushing P was a thing for a few years. I don't know. It's gone at this point. Why do I want you guys to be thinking the letter P right now when I'm asking how do I draw this line? Perpendicularly, right? We always measure and stuff 90 degrees if possible. So you're right, Lily. It will be vertical here. But I wanted that perpendicular part is really what I'm after. So if we eyeballed and we reflected first, and you guys just help me, it's not going to be perfect. And we'll see. I don't know. Everything I do is perfect. You guys tell me when you think it's about the same on both sides of this purple line. Does Y, would you believe it if I said here? Z, would you believe it if I said here? W, and I'm just going to try to draw this. We're just eyeballing out. You tell me when to stop. Here it is to W. Up or down from here? Or is that good? That looks about believable to me. And then X would be somewhere up here, right? Now, if we get to this, and that is much better than I was expecting. Oh, we're close. That's where that point should have been. So we're going to pretend like it was all along. That one was much better. Do they look like they're the same shape? Okay. We just spent way more time, and I spent way more time talking about that. I just want to remind you, we did do this with compasses and straight edges, right? Not compass, protractor. Okay, so I don't remember what the original question was at this point. I've been talking for so long that no idea. What am I talking about? Okay, so we could reflect it, and then we would do what? Dilate. What point do you think we would dilate about if we did this? Ooh, that's a good question, I think. Talk with your neighbors, 30 seconds. If I do my reflection first, which is what I've drawn on the board, I now need to dilate. Where should the center of dilation be if this is the route we take? 30 seconds, real quiet with your neighbor. You have a few choices. If it's a guess, that's okay, but I'm going to make it better. What do you think? So if I picked y prime right now to dilate about, if I made that my center, I almost fell. If I made that my center, how far would the distance between y and y prime be? Or like it wouldn't move, would it? Like yesterday, is this your all math? If we go back to one that we've drawn, do you remember what the center of dilation was here? So read through it real quick and tell me. And that happened to be A, right? Yeah. When we dilated about point A, what point didn't move? Which point don't I want to move here? So what do you think we should have to dilate about? Boom, and we got it. Did you hear what we were speaking about? Or do you know the answer? Do you have an answer? Okay, can I steal a problem from yesterday? Yeah. Okay, I'm going to steal this one from yours, but we're going to finish it because you didn't put the other points on here, and that's okay. Your other ones came out like this, roughly. Wow. It came out about like this, I think. Halfway, so it would be like there. Like there's where our new shape came out. Oh, yeah. What was the center of dilation on this one? About the point -6.5, right? Mm-hmm. If we dilate about A, did it move? What point don't we want to move here? So what point should we dilate about? Love it. We got it. Like it's that easy from it. Okay. So checking stuff out. Uh-oh. Who did I talk to? Ashley, is there a style? Nope, it's right here. Got me good. Okay. So if we look at the example from yesterday, and I don't know the example, I think it was yesterday, we have one where we have a shape like this, and we dilated it by a factor of like 1/2 from this point. When we do the image, we wound up getting this. And this point, when I dilated about it, didn't do anything. It just stayed, right? What point do I want to stay here? Z. So if we're trying to get this one, the same thing that we did last time, we would reflect over this horizontal line, and then we dilate by a factor of 1/2, you guys told me. About which point? Z. Okay, looking at these, is it crazy difficult to find these? Do you think it could be? It could probably get worse with these. Love this. Last one, maybe. We're pretty much near the end of this. We are so close. Yep, one more problem. And we're just going to draw this one out. So you are going to hate your drawings, and that's okay. Last example, I just want to ask, similar? And we'll talk about that. Cool. So we get a little bit of new notation, and we might have used this year. Unfortunately, I'm not the best circle drawer, but I don't think you guys probably are either. But I am, in all reality, because I don't have to draw them. So I'm going to use this really quick. You know what? We'll just do bad circles. Here we go. I want to know this circle. It's beautiful. And what should we call the center of this circle? C is a good choice. Here's a circle whose center is C. And if I want you to draw any particular circle, you would need a center point. And anything else you would need? If we want it to be really, truly the same size, we'd need a radius. Now, I'm just going to call it R for now. Okay. Now, over here, we have another wonderful circle. And its center, we'll say, is at Q. And for just the sake of this, I'm going to have another radius, but it's not the same. Now, we have some choices here. I'm going to call it S right now. My only question for you is, are these similar? And it's yes or no, but I want you to justify it. Convince me whether this little circle is similar to the big one. Now, notationally, the way that we write these, we've used circles in here and never. I honestly don't remember. Probably not much. Okay, the way that we talk about this one, and it seems so silly. If we want to write a triangle, it's triangle ABC. We see the points, right? I don't have points. I mean, I have infinitely many points, but I can't just name the vertices of this. The way that we write circles is circle like this. And what's the center of this circle? C. We have a circle with center C. Now, if I had concentric circles, which meant like a bullseye, a circle with a bigger circle, and they all shared the same center point, I would have to specify which radius, but there's only one. So my question right now is this similar to the circle with which center? Q. So there's our question. I want you guys to chat about it. I'll give you like 60 seconds. I'm looking for a yes or no along with a justification. Should we do a little switching seats around, or do you want to talk with your regular neighbors? Okay. Caveman, let's chat. The formal definition of similarity that we've seen, and we'll clean this up, but we said today that we talked about a mapping between them that's proportionality is kept. Like, that's another way to word it. Everything is the same. Now, the very first time we wrote it, we used 4 total words. Same, I guess 2 for this. Same what? And like, that's a weird way to word it. Congruence is same shape, same size. What's similar? Same shape and different size, right? But same shape is really what I'm after. If we look at these things, if I say, imagine a triangle, is it very likely that all 9 of us in the room right now imagined the same triangle? You say yes, Ashley, I think. Did you say yes? Do me a favor. On the count of 3, you're going to sketch a triangle in your margin, and I'm going to sketch a triangle up here. Okay, you ready? 1, 2, 3, sketch a triangle. Yep, sure. Can I borrow this? I'm not going to borrow all of yours. Did we all draw triangles? But can we really say they're all the same shape? They have the same name, but there's my triangle. Is that the same shape, but just a different size as Lily's triangle? Or are they like noticeably different triangles? Different. Now, so we can't just say all triangles are similar, right? That statement is nonsense, and we just showed in that counter example. Here's my other challenge, though. Draw a circle on the count of 3 on your page. And assuming that we're not like nitpicking and saying that's a terrible circle, Carson, or Holloway, or whomever, did we all draw the exact same shape? probably different sizes, but there's no chance that we've drawn different shapes because every circle is circular shaped. Like triangles have variation, these don't. So as we're looking at this, Carson said right away that yes, they are similar because all circles are similar. And this book does not do that. In past books, that's a theorem. So congratulations, we have Carson's theorem at play all of a sudden. Good work. All circles are similar to each other. Now, Carson even went a step further. If we look at this mapping, and I know that I didn't specify, we can't tell which one is image and which one is pre-image. I have no preference. Raylene, which one of these is the image? And there's not a right answer, it's just choice. This, yeah, I assume you mean the right. Okay, so if this is my image, that means that this was my pre-image. And you even added a little bit more information to yours, Carson. Do you remember what else you said?
It was something like the radius, if the R is 1 and the S is 2, the scale factor is 2.
Love it. Now, I'm going to clean that up a little bit, but you're absolutely right. Not only are all circles similar to each other, but the scale factor that we're looking for, which we could write K, is what we've been doing. If it all of a sudden changes to N and it's just a different letter, but we still say this is a scale factor, does any of the math that we've been doing change? No, just a different letter. The scale factor K for these particular situations is we only have one length given right now. What's the length that we're given on this image? S, which is the radius of the big circle, over what's the radius of the small circle? R. And whether we call it 1 or 2 or it doesn't matter, Carson, we're doing exactly what you said. We have a generalized way to talk about these. So, good news, or I guess bad news, sorry, is that class is over. The good news is that this weekend, so that you don't have to forget about everything and cry all day Monday because we don't get geometry, you can start and finish homework 7.2, which you'll find on page 319. And this section feels good or bad? Okay? All right. So let's do 15 through 23 odd. And 12. Cool, cool. You guys have a wonderful day. I know I'll see you all later at 3 o'clock when the door opens for chess club today, so you can come and learn and play with all your friends and classmates and stuff. 3 o'clock is chess club. Come check it out if you haven't. Otherwise, I'll see you cool cats and kittens on Tuesday. Enjoy your day off.